Hello everyone and welcome to another lecture on this course on line commutated and PWM rectifiers. In the last lecture we had discussed more about like sine PWM and how it can be used for voltage source converters. Today we will learn more about the steady state operation of the voltage source converters and how that is used to exchange power with the, for example, with a grid. Okay, so we are in this week, third week, and we are going to focus more on this steady state analysis, phasor diagram, leading, lagging, and unity power factor operation, a little bit of also the regenerative mode. These are the things we will cover in details. So if we look into what we have already discussed, is that, for example, a voltage source converter, in short VSC, the VSC, when it is connected to the grid, can be represented by this with this circuit diagram, where this box, which is this voltage source converter, typically a three-phase voltage source converter, typically looks like this. Okay, so there are like these half bridges working together using, for example, sine PWM. You can also run the VSC with space vector PWM. This is also possible, and we will take it up a little bit later. As of now, let us see that let us assume that we are working with sine PWM. So this circuit here, which we have in this circuit of the VSC, and here is the grid, and then we have the filter. Okay, filter is represented as an RF and LF. Okay, the inductor, the resistive part of that inductor is the RF. Okay, now this circuit here is basically can be, as we had discussed in the last lecture, this can be the equivalent circuit is something like this. Okay, where the VSC is now represented by the three-phase controllable voltage source. Okay, and which are given by this VAN, VBN, and VCN. So suppose we use sine PWM, using that technique, the magnitude, angle, and frequency of VAN, VBN, and VCN are adjusted. So it is a completely adjustable or controllable voltage source. And now we are going to connect it to the grid, and we will now see at steady state how we can adjust this voltage source or this the VAN, VBN, and VCN. How do we adjust it so that we can exchange a certain amount of active and reactive power with the grid? So this will be the discussion today. This discussion is equally valid for a motor control application. As I have repeatedly said, that suppose we use a PMSM, then this is the back EMF of this PMSM, and this is the synchronous reactance. Okay, so a voltage source converter can be similarly, some changes in the control logic will happen. Okay, because there will be some cross coupling terms and all in the dynamic model, but essentially the understanding of a grid connected converter and for a motor control drive, the understanding of this technique is very, very similar for both the applications. Okay, so if I write down the governing differential equations, okay, so then we can easily write it. VAN is RFIG. Okay, this VAN is RFIG plus LDIdt. Okay, plus VAG. Okay, so this is how the equations are written, and then we can also rearrange the terms and write it like this way. Okay, the reason for writing it in this format will be evident at some point later when we will do the dynamic modeling. For now, Okay, so this is typically of the format x dot equal to ax plus bu, right, in the matrix format, state space variable format. So we will take it up later, but for now just assume that this is the way we are writing this equation. And at steady state, what happens is that this differential equation will now be written on a per phase basis, assuming sinusoidal quantities. So this VAN, which was an instantaneous quantities, now will all become a phasor, okay, at steady state, right? So then this RF IAG, this quantity will now become IAG phasor, and this LDIDT will become J omega LF IAG, and of course VAG will become the VAG phasor. Okay, so therefore this is the when we want to analyze the grid connected VSC, we actually always use this equation at steady state. Okay, Vn RFIG, and so this equation, if you understand, it will be immediately leading us to how we will actually transfer energy between the converter and the grid. Basically, remember, what is this VSC doing? The VSC is connected to some kind of a, so I'll give you some examples. VSC is connected, supposed to a PV. Okay, so there is a PV on the DC link of the VSC, and we want to take the power which is being generated by the PV panels, and we want to feed it to the grid, right? So therefore, at steady state, this will be the governing equation, okay, for that. Again, on the other hand, suppose we have a battery on the DC link of the VSC, and we want to kind of like charge or discharge the battery from the grid, right? Again, the same set of equations at steady state is applicable. Okay, this equation which I have just now written is also something which you must have studied in some BTech courses. Okay, this is very similar to how a synchronous machine is connected to infinite bus bar. So we are not doing anything new here. Actually, we are repeating what we already know. So in a synchronous machine, for example, you have a back EMF, and then you have the synchronous reactance, and then you have the infinite bus bar. And accordingly, you can now understand that basically you have two AC sources which are connected through an impedance. Okay, so this is the basic analysis. And then you have this one as V1, and then you have V2. Okay, one of them usually is controllable. So in case of synchronous machine, the E or the back EMF is something which is controllable. In case of a voltage source converter, the fundamental voltage that is produced by the VSC, which is the one which is controllable, and that is controllable through sign PWM or space vector PWM. Okay, and then yeah, then there is also the grid, which is basically a step source, right? So now the question is, how do we exchange P and Q with this grid? Okay, and you can also kind of like start thinking that we already know how synchronous machine reacts with the infinite bus bar. Okay, so this E can lead or lag the infinite bus bar voltage. Okay, the grid voltage, it can lead, lag. So we have this 4-quadrant operation of the E versus V. Okay, the 4-quadrant operation of synchronous machine. 4-quadrant operation of synchronous machine is something which we already kind of like know, this one, where E can be leading or lagging to the terminal voltage. Exactly similarly, here also we will see the same thing happening. So let us see what is the phasor diagram, and you can see here the per phase phasor diagram is shown below. Okay, and because this is coming from this equation here, VAN, VAN is equal to VAG plus RFIG plus J omega LF IAG, right? So we can draw this phasor diagram here. Okay, here is your VAG, this is the grid voltage, and this one is the converter voltage. This is controllable. Okay, So we can basically move this VAN voltage like this way, okay, clockwise or anti-clockwise. We can also do is that what we can do is we can reduce the size of VAN, okay. So we can make this delta angle adjust, okay, and we can also change the length of this phasor, right? So the way we do it, the reason, what is the effect of doing this change in the VAN is that it will change the amount of P and Q that we are exchanging with the grid, okay. And what does it mean? That the grid will see leading, lagging or unity power factor operation. We'll see this one, okay. So suppose I want to change this to a unity power factor operation. So how will I do this? You can see here, I can draw this one like VAG here, okay, and I want a unity power factor. So then this current will become IAG, right? This is a unity power factor with the grid current, and so this will be the okay. So first we will have the RF, and so then you will have RF IAG here, okay, and then you have the J omega LF IAG here, and then of course you will draw VAN here, okay. So you can see that by adjusting VAN, the current that was now lagging has become like a unity power factor current, okay, with respect to the grid voltage. So this is definitely possible because VAN is something which is in our control. That is something which we can, at our own will, we can actually move it, okay, left, right, we can increase the length and so on. So I'll give you one example here. Is suppose I am going to work in a situation where there is a VSC like this, okay, which is here, and then there is a PV panel here, okay, PV panel connected to the VSC, and we have this one and connected to the grid, okay. So this is not a single PV panel. A single PV panel will have a very less voltage and not much of power. So probably we will have one PV panel is coming as of 2025, like the voltage is like between 40 to 50 volt, that is the open circuit voltage, and the power may be between 300 to 400 watt, one panel. So actually this is not a single panel here, so multiple panels, several panels are here series connected so that we get adequate voltage. This is called single stage conversion. We also have double stage conversion with a boost converter, but we will not go into those details right now. So we have this PV here and we have a VSC and we are connecting to the grid, okay. This L, this inductor, can also be part of a transformer, okay, because we will often need a isolation as per grid standard, okay, between the VSC and the grid. But the transformer can also be represented by a series RL circuit. So in this case, suppose we want to keep the, suppose this PV panel is generating active power, okay, and so this in the first condition, if you see the phasor diagram, this is the first condition, and the steady state phasor is something like this, okay. Here this RF IAG comes and then J omega LF IAG comes here, and here is the steady state phasor diagram that we have, right. And so the power that is basically being injected into the grid from this VSC is basically this voltage VAG and then IAG1 into cosine of the angle between VA and IA, right. So this is the power which is being injected, okay. Now suddenly suppose a voltage sag in the grid happens. Now there is a certain, when you connect this kind of a PV coupled VSC to the grid, there are certain functionalities which are needed. One of the, of course, is the functionality that whatever is the PV generated power, we want to inject it into the grid. because that is why we are doing all this stuff. We want to extract the energy from the PV panel and feed it to the grid. Okay, so of course that is the primary function, but there are some secondary functions which are also required from such VSCs. One of the secondary functions which is also very important is to supply a certain reactive power when some sag in the grid happens, voltage sag in the grid happens. So this is basically coming as a standard. In most of the modern standards, this is kind of a requirement that if there is a sag in the three-phase, suppose this is also three-phase grid, if there is a sag in the three-phase grid, for certain duration and for certain magnitude of the sag, certain amount of reactive power must be injected from the VSC into the grid. Okay, now then what happens to the operation of the VSC? Now we have understood that okay, the VSC is now working like this, okay, with this kind of a phasor diagram. Okay, now we want to inject a reactive power from the VSC. Note now here what is the reactive power of which is now supplied initially. Initially the VSC is already supplying this much of the reactive power. Okay, and so because you see here this projection corresponding to IAG cos phi. Okay, IAG cos phi is constant. Okay, the active power from the PV is constant, whereas at this point the IAG sin phi, this is proportional to IAG1 sin phi. This is what is the reactive power being exchanged with the grid at this point of time. Now we need more reactive power from the grid. Okay, and this is we need more reactive power needed from the VSC, and we have to inject it into the grid because the grid requires this reactive power to mitigate the sag. So what do we do now? Remember, we don't want the active power to change. Okay, we cannot change the active power, okay, because there is also a DC link here. Okay, so we don't want to change the active power, and so what will happen here is that we will move our current phasor into this position IAG2. Okay, so this 2 is the second position, so in such a way that this projection IAG2 cos phi, this projection remains the same as before. Okay, so IAG1 cos phi 1 is equal to IAG2 cos phi 2, so that the active power remains the same. Okay, because the PV is generating the same active power. Okay, so it must be maintained constant. But now we want more reactive power, right? So therefore this projection, which is corresponding to this projection, this is corresponding to IAG2 sin phi, this is increasing. Okay, this is increasing now. So if we operate on this line, so if we operate on this line here, okay, on this line if we operate, then we can see that we can actually have several types of, so we can have several such phasors possible, all of them having the same active power. Okay, but the reactive power is changing. Okay, and this will help us to kind of like feed reactive power, variable reactive power from the VSC into the grid. Okay, but how am I achieving this change of the current phasor? This we are achieving by changing this phasor VAN1 to this one. Okay, so we have actually, because this is the only controllable variable, okay, we only have control over the converter voltage, and the converter voltage moves from this point to this point here. Okay, that is how the change of the current will take place, keeping the active power same. Of course, this is done through a closed loop control. This does, we can also do it in open loop, but we have to be very, very careful and calculate and all. Rather, we will do it using a closed loop, because then we can do it very fast without much of an overshoot and all. But basically, when the two, if you analyze the two steady states, basically what you have done is you have moved the VAN phasor, the fundamental voltage, from the grid, from the VSC. This is where the fundamental voltage comes here, okay, VAN. This voltage I have adjusted, okay, and that I have adjusted from this point 1 to the point 2, and accordingly everything else changes in the phasor diagram. And so I can momentarily change the reactive power supplied from the VSC into the grid, keeping the active power constant. Okay, so this is possible. What is the other thing? Of course, the question comes in our mind, can I do the other thing, like can I make a constant reactive power and a variable active power? Yes. Okay, so it is also possible. So the reactive power can be kept constant while the active power is changed. So this is also possible. So how do we do this? Okay, so active power is changed. So you can see here in the phasor, right? You see this projection, this is corresponding to IAG sine phi, and this is the reactive power, and that remains constant, whereas the active power here, so this will be corresponding to P1 and this will be corresponding to P2. Okay, so the active power is changing. Okay, and when do we need such an operation? Okay, that operation will be needed because suppose this PV source is the same PV source, it will throughout the day it will not generate the same active power. In the morning it will generate less, in the afternoon it will generate more, and again in the evening it will generate less, right? So therefore when the active power is changing, we have to follow a certain phasor diagram. If we analyze that change in the phasor diagram, we will see the changes in the phasor diagram, and this can be again achieved like so. This was the VAN point and this is the VAN2 point. Okay, so we have changed the tip of the phasor from VAN1 to VAN2. We have moved the phasor and we have changed the phasor length of. Okay, so that is how we can actually adjust the movement of the phasor. The question is how fast we move that operating point from one steady state to another is dependent on the controller. So how fast we move from here to here is all dependent on the controller. Okay, and we will study this controller somewhat in details. Okay, so therefore we can say that the movement, okay, so if you talk from the energy point of view, okay, these are the two stable energy points, okay, VAN1 and VAN2, where energy balance happens between the grid and the VSC. So they will be operating nicely at these 2 points. However, during the transient condition, okay, there will be some fluctuation of the energy, and the transient condition will come only when we do the dynamic modeling. Once we do dynamic modeling and design the controller, then we will see under transient condition how these things move. Of course, during dynamic condition, we will not use phasors anymore. Phasors are valid for steady state operation. During dynamic condition, we will use space vectors. Okay, and so we will have to analyze very similar analysis, but it will be slightly different. We will use the space vectors for the dynamic conditions. Okay, and now so let us little bit look into what is the power which is flowing. Of course, the active power flowing into the grid, PAG, is this VAG into IAG star. Okay, real part of that. And if you expand this part and take out the real part of it, okay, real part is here, and simplify this one, then we see that the converter, the power generated or the power delivered by the converter is the power absorbed by the grid plus the power which is getting dissipated in the resistance, right? In a similar way, the reactive power absorbed by the grid is imaginary part of VAG into IAG star. And again, if you simplify, then you will see the reactive power delivered by the converter is QAG plus IAG square omega into LF or IAG square X. So this is for per phase quantities, right? So these are all per phase expressions, and then it must be multiplied by 3 so as to get 3 phase expressions, right? Okay, fine. So now then we say that, okay, now we are actually now expanding our operation, and as you can understand, now we are talking about a 4-quadrant operation. Of course, this has very much similarity with the synchronous machine, okay, and synchronous machines can also operate at 4 quadrants. So this VSC can also operate in the 4 quadrants, right? 4 quadrants means what? The how we transfer power from P grid to Q grid and like that, okay. So for example, here VAG and IAG, these are lagging, okay, and then so you can always say like this is the VI star, okay. So if you do the VI star, then we say that this here the P is positive and Q is positive, okay, VI star. So I star means I comes here, okay, and therefore P is positive and Q is positive. Similarly here if you see PI star, so then the PI star is here, okay, and here therefore P is negative and Q is positive, okay. So this is how it will happen, okay. So therefore you can find it out yourself, right? So now we see, so of course this is only possible if the VSC is supported by a battery, okay, because unless there is a battery, okay, you cannot draw. I mean here we are assuming that the VSC is able to deliver or absorb whatever amount of P and Q it is being asked to do that, okay. And this can only happen, of course, if you have a battery or an energy source which is connected to the PV, okay, like energy source means a battery or a fuel cell or something like that, okay. If you have an energy source which is connected to the PV, then you can exchange whatever P and Q you are being asked to. But suppose we do not have a battery, suppose we have a capacitor in the DC bus which is called STATCOM, okay. So if it is a STATCOM, what will happen is, suppose this is an ideal STATCOM where there is no active power loss, okay, if P is 0. So in a ideal STATCOM, so P equal to 0 and Q is variable, okay. This is what happens in a STATCOM. A STATCOM is a static compensator. This is usually used in the grid for improving the power factor. And so here P is ideally 0. In practical STATCOM, P is required for taking care of the losses in it. So then what happens is, if you take a STATCOM, then basically you are working on this line, okay. You're basically working on this line. It's the Q. So you will move your phasors in such a way that you are always working on this Q, okay, right? Acha. Now another point is, suppose you have, so now we come to our PWM rectifier. So what does PWM rectifier means? PWM rectifier means P is absorbed by the VSC, right? But now this becomes very simple for you to understand that P absorbed by the VSC, which means that P grid is negative, right? So the grid is supplying power, right, and the VSC is absorbing power. So if P is absorbed, so we will be operating in this quadrant and this quadrant, okay, where the grid is supplying power to the VSC. But this is essentially a limited 2-quadrant operation of the VSC. The VSC with a battery can actually work like a wonderful 4-quadrant converter. Okay, so therefore the word PWM rectifier is a limiting word. Okay, it does not encompass the whole of the operation of the converter, and so we should rather use the word PWM converter. Okay, because it can work in 4 quadrants with a energy source on the DC link. If you do not have the energy source, like if you have a capacitor on the DC link, then you will not be able to do this, right? Then you will be only operating with P equal to 0 and Q as a variable thing. Okay, so that is what we understand from this one, and this is kind of like summarized in the following slide, where we say that VSC, which is supported by a battery, is a 4-quadrant converter which can deliver or absorb power from the grid. Okay, power can be negative provided the DC bus has the capacity to absorb the power. Now this useful during regeneration. What is regeneration? Suppose we are now thinking that this VSC with a battery can also drive a motor load, for example in electric vehicles, right? In electric vehicles we have a battery on the DC link and we have a motor on the other side. So in an electric vehicle, you can see here, so this goes to say a PMSM here or an induction motor, whatever. Okay, so we have the EV. So this is the battery. So when the induction motor is in the motoring mode, that is, it is driving the wheels of the car, then the power is going this way. But when the EV is going down the slope, for example, then we have a chance to do a regenerative braking, which means when it is going down the slope, the gravity, so it is getting the gravitational is the kinetic energy, we can feed it back into the battery so as to save some energy. Okay, otherwise what will happen, the car will actually accelerate very fast, right? So we need to brake it. The way we need to brake it is that we convert that energy or the kinetic energy of the car into an electrical energy, which is again fed back to the battery. Okay, so then the energy will flow like this, okay, from the motor. So then the motor no longer behaves as a motor, or the machine no longer behaves as a motor, the machine behaves as a generator. Okay, and that can be fed back into the battery. Okay, this is done very simply using the control over the VSC. Okay, so the VSC is basically controlled, and it can be controlled to either flow the energy from the battery to the machine or from the machine into the battery. Okay, so that way, so during regeneration also you can feed it back into the battery. Okay, the VSC has a limitation on the maximum output voltage and maximum output current. Of course, the VSC is made up of power converters, power devices, and all the such power devices have a maximum voltage capacity and a maximum current capacity, and the VSC will be of course dictated, or VSC will be bound by those capacity which is imposed by the power devices. Okay, the voltage capacity and the current capacity. Okay, so the above points are also valid for the VSC drives a motor load. This is true. Okay, now another part of this is very interesting. This actually combines both sides of the grid and the motor. Okay, so this is called the back-to-back VSC, and I will just explain what this means actually. Okay, what is a back-to-back VSC? A back-to-back VSC is, there are two VSCs. Okay, VSC1, VSC2. They are connected by the DC link here. Okay, so the VSC2 is driving a motor, and the VSC1 is facing the grid through a filter. Okay, now the connecting point between these two is the DC bus or the DC link. Okay, so how does this thing works? So this is very common in many applications. Okay, in motor drive applications, you have a grid, so the energy flows, the energy can flow both ways. Okay, the energy can flow both ways. Okay, from the grid into the motor, or from the motor during regeneration into the grid. Okay, so the energy can flow. But how does this thing work? Okay, so suppose we look into the VSC2. Okay, this VSC2 basically, actually the VSC2 and the VSC1, they work independently, so they do not communicate with each other. It is not necessary for them to communicate, because the exchange of their energy can be obtained by observing the DC bus. Okay, there is no need for them to communicate. So VSC2 basically does not care about what VSC1 is doing. Okay, so basically it only controls the motor, and we know what are the different control techniques for the motor. For example, V by F is one technique by which VSC2 can be controlled to control the speed of the motor. Then we have this vector control or the field oriented control, okay, in which we control the torque and flux of the motor. Okay, so we can have these types of control which is working in VSC2. VSC2 just looks into the motor control, assuming that this DC bus here is fixed and constant. Okay, but how does VSC1 operate? Okay, the VSC1 controls the power required from the grid. Okay, so VSC1, what it does is, it is facing the grid and it sees that how much power I need from the grid. Okay, remember the motor is basically consuming, so under normal condition the motor is absorbing the power. So when it absorbs the power, okay, what will happen, the first impact of that will be on this DC bus. Okay, because you are taking the energy from the DC bus into the motor, and so the DC bus voltage will fall. Okay, the stored energy in the capacitor, it will start to fall. So then what does VSC1 do? VSC1 actually monitors this DC bus, and when it sees that the DC bus voltage is falling from its nominal value, then it can take power from the grid and put it into the DC bus once more. Okay, and this we have seen how the VSC1, by changing this voltage, this is that VAN, the phasor diagram between these two we have covered. We have covered the phasor diagram here in few slides. Phasor diagram I have covered a few slides back. Okay, so by adjusting that phasor VA, okay, it can control the P and Q from the grid, right? So therefore, what does VSC1 do? VSC1 basically only sees this DC bus, and then VSC1 will monitor this DC bus and will ask or will make sure that the requisite amount of P and Q is drawn from the grid. Q is not necessary. Okay, Q is, we can make Q equal to 0. Usually Q is made 0, which means we are operating at unity power factor. Okay, but Q can be used. Okay, you can have a non-unity power factor also. But VSC1 monitors the DC bus, and if it sees that the DC bus is falling, it will ask for more P from the grid. If the DC bus is rising, then it will say that, okay, I do not require so much of P, let me reduce the value of P. This is also useful during regeneration. Suppose you have a regenerating condition. Suppose now we are taking about a regeneration from the motor. Okay, so regeneration means P is going back. Okay, so the motor is now feeding back the power here. So this power will come here, and this will cause the DC bus to go up. DC bus will go up, because now you are pumping in energy from your motor into the DC bus. So based on half CV square, the voltage on the capacitor will start to rise. So now what VSC1 has to do, this fellow here, VSC1, it will monitor this DC bus, and it is seeing that no, my DC bus is increasing rapidly, and at some point it can destroy my devices, okay, because the IGBT or the MOSFETs which are there inside VSC1 and VSC2 must be rated for the DC link voltage, right? So it will see that okay, and the DC bus is rising very fast. So now what I have to do is I have to put this P back into the grid, okay? So then accordingly it will change these phasors here, okay? The phasor quantities at steady state, of course, VA, VB, VC, these phasors have to be changed with respect to the grid phasors such that this power is now getting back into the grid. And this is how at steady state the regeneration power which is coming from the motor must be equal to the power which is fed into the grid, assuming 100% efficiency in the both the VSCs. Okay, so this is how this is a very classic example of two VSCs working together without communicating with each other, but the DC link is kind of like the source of contact or the point of contact between the two converters. Okay, so I'll take up quickly two examples which will kind of like help you to understand this thing. So there is a single phase converter. There is a single phase converter here shown in the figure which is connected to the 50 Hertz grid. So there is a grid 50 Hertz. The magnitude and angles of the grid voltage, converter voltage and line inductance are given like this. Okay, so Vs is 230 angle 0, then this is Vg is 250 angle delta, and this L is equal to 5 millihenry. Okay, now assuming the grid power factor is unity. Okay, now the first question is, what is the phase difference between converter voltage and grid voltage? Okay, so basically the value of the delta, okay, the delta which we have used here, this delta, what is the value of the delta here? And in order to solve this, it is the most easy way or the easiest way is to draw the phasor diagram. So we can just write like this here. So then we can say that Vs minus JIGX is equal to Vg, right? This is the thing, and the grid power factor is unity. So let us draw the phasor diagram. So we will draw it here. Here is the grid voltage, and Ig is something here which is at unity power factor, and so this is JIGX, right? And here is my Vs, and this is the angle delta. Okay, so once we know this phasor diagram, it is now very easy for us to either write the equations or diagrammatically solve the steady state operation. So we can write it Vs minus JIX equal to Vg, hence we just write 250 angle delta minus JIG0, Ig is at 0 angle, and this is the X, okay, this 1.57 is basically 2 pi into 50 into what is L, L is 5 millihenry equal to X, okay, so that is how much it will come, okay, and that will be equal to 230 angle 0, right, because Vg is 230 angle 0, single phase operation. So the equating the real part of this equation, so we have the real and imaginary part of this equation, and therefore we get delta equal to 23.07 degree. Second part of the question, what is the magnitude of the current injected? Of course, we can again equate the imaginary part of the previous equation, and we'll just get Ig equal to 62.4 ampere. Okay. Now the third part of the question, what is the active power supplied to the grid? Okay, how much is the active power supplied to the grid? So you have to remember that so in this case the grid power is, or rather I should say SG is VG into IG star. Okay, and PG is equal to real part of SG, and of course QG equal to imaginary part of SG. Okay, SG is VG into IG star. So therefore PG is equal to real part of VG IG star, and therefore we just write 230 angle 0 and 62.4 angle 0 because they are at unity power factor, and so this will be equal to 14.35 kilowatt. Now what is the reactive power supplied by the converter? Okay, supplied by the converter. This is important, not important, because the reactive power supplied, so in this case of course QG equal to 0. Okay, the grid, because the grid power factor is unity. Okay, so therefore the whatever but the converter is supplying some reactive power, and this reactive power is basically all absorbed by the inductor. Okay, the filtered inductor. Okay, we have assumed a filtered inductor with negligible resistance in this case. So what is the reactive power supplied by the converter? So QS, okay, here is imaginary part of VS into IG star. Okay, so this voltage and this current here, IG, VS into IG star. Okay, and then you put these values here, and which comes out to be 6.11 kilowatt. In fact, this should be absorbed by the inductor, should be absorbed by L. Okay, it must be, because we are not injecting anything to the grid, then no reactive power being injected into the grid, and so the entire reactive power must be consumed by the line inductor. Indeed, so if you just do it double check, Ig square into X, okay, this is the reactive power being absorbed by the filtered inductor. So Ig square into X is also 6.5. So this and this are equal. Okay, this value and this value are equal. Okay, so that verifies that yes, whatever the converter supplied reactive power is entirely absorbed by the inductor. And then there is a last example which we will quickly do. Okay, three-phase converter is connected to a balanced line voltage 50 Hz gauge as shown in the figure. The value of the filtered inductance is 1 millihenry, and assume RF equal to 0. Okay, this is very similar to the previous example, but now we are considering a three-phase example. Okay, so this value RF is almost 0. Okay, when negligible. The line current for phase A is given as this much. Okay, so the line current is given. Now this is very similar to the previous, but now we will do the three-phase calculation. So what is the RMS value of the line voltage of the converter? Okay, so in order to do that, we assume that the per phase grid voltage, so this is line 11 kV is a line voltage here. Okay, so therefore VAG, okay, will be 11 into 3 by, this is the line voltage. Okay, VAG phase voltage will be 11 kV divided by root 3, right? So that is what is 6351 volt angle 0. Okay, we are assuming the phase voltage to be at an angle 0, and then we just apply the previous formula on a per phase basis. Okay, it is always useful to do it on a per phase basis, the calculation, because this is the balanced system. And so VAN minus j IGX equal to VAG, and therefore VAN is this much plus this much. Okay, and so VAN comes out to be 6513 at an angle 2.4 degree. Okay, so you can see here a little bit of delta. This is a very small value of delta, 2.4 degree only. Okay, but it can cause a good amount of power to be exchanged. Okay, so 6513 here, and hence line voltage of the converter is 11.28 kV, slightly more than the 11 kV value. Okay, and then what are the three-phase active and reactive power supplied to the grid? Okay, so you can always get it, S grid is 3 VAG IAG star. Okay, so therefore this will be equal to 3 into 6350 651 at an angle, so this is VAG, 3 is because of the 3 phase, and then 1000 at an angle 30. Okay, IAG star. And so when you put it, this will come out to be this much, 16.5 megawatt and 9.52 megawatt. Okay, so this is the answer of how much is the 3-phase active and reactive power supplied to the grid. You can find it out yourself. So yeah, so this is the end. So today we actually studied on the steady state operation of the voltage source converter, and we understood that this, with a DC link, stiff DC link or a battery, the voltage source converter is basically a 4-quadrant converter, and it can exchange P and Q as per commanded, okay, as we command it. And so it will be able to exchange certain active and reactive power depending on how we place the phasors, okay, active the fundamental voltage phasors. And slowly now from next lecture onwards, first we will talk a little bit about hysteresis control, and then we will slowly move into something called as space vectors, and then dynamic model of the VSC. Thank you.